I put this kind of tutorial together to do a fair coverage of parallel computing, basically, and at several levels, basically to take research grade code and speed it up and go to parallel. There's several levels to going parallel, basically, and Python gives you many different ways of doing that. So we're going to take a shot across the bow at a lot of them. One of the first things that you're also going to be interested in doing when you go to parallel is make sure the code you're taking to parallel is actually efficient, because that's the place where you get the most time savings, right? If you put slow ass code out there in parallel, it's basically going to be slow n times, and the biggest time saving that you're going to have is to speed that thing up. So I had a particular coding job that I was doing that was it's part of a project that was multiple. So it was a earthquake simulation on a structure, truss structure, a bridge basically, or electrical towers, something like that, and the standard code. There was an open source standard code, and it ran, in a second or so, and I could just use it and have that thing run in parallel. But what I was going to do is do an optimization on the code, parameter optimization, and then a higher level optimization on top of that. So the thing was going to be running, in an optimization, which is a pretty serial process, and then n optimizations on top of that. So we're talking about now, maybe 200,000 invocations of this thing, where it takes a second each time, and that becomes way too long, right? So the thing I had to do was say, all right, I have to sit down and rewrite this open source standard thing to shave off as much time as I can. And I was able to trim a reasonable simulation of the thing down to 1/10 of a second, which ended up making the difference between being able to run it on a large-scale supercomputer versus not being able to fit in the queues. So you have to do those kind of things. That's actually the most important part. And if you write your code to be efficient and test, so you know where the hotspots are and what you can work on, you'll find that there's a lot of strategies for then accelerating the code to parallel and high performance. So I wanted to start with a motivating example. This is example I found found here on pythonprogramming.net that I modified a little bit at Monte Carlo Yo. So I modified it, and it's going to be something that we'll come back to a couple times. And basically, it's a betting strategies tester where there's a couple different betting strategies. And the lowest level of the betting strategies are rolling a die. So here's rolling a die, where we roll the die once, pick a random integer, and then it's slightly biased. So we then check and see if we win or not. And let's see, since I have no idea what's on here, I have to run everything. Okay, so, and then I should be able to do that, yeah, and it ran. Okay, so there we get a lot of ones and zeros. And then and then here's we have a bunch of different strategies. So here's here's a roll or dice. So we have use roll to test this, where it runs several times, and in a for loop, and that's what I use to roll the die several times. So we'll come back, and that's a good thing that we can check. So anytime you see a for loop, we're talking about. No, awesome. Yeah, it's still a spinny ball, but that's better. Okay. So for loop is a good place for parallel computing. It's actually the basis for it, for batch parallel. And here is a couple of our different strategies that we have. They're a while loop again. So here's another loop. It's basically going to be a loop over the number of a number of die rolls, where basically what happens is if you get a 1, that's success, and you win, and if you get a 0, then you basically lose that turn. So, the thing about this is we're not actually playing in the time that we're rolling the die. The rolling the die is independent of any of the previous outcomes before. So we can think of already in parallel strategies, are we going to roll the die, as a vector? We're going to roll the die the whole time first up front, and then have the algorithm react. But right now what we have is just rolling a single die every time, and then checking what happens, and then checking our money up or down, basically. Okay, so this is a simple strategy that basically so it's a simple strategy that if you win, you always bet the same amount, whether you win or lose. So that's a reasonably parallel strategy. Here is another strategy called the martingale strategy, where basically it depends on what happens the last time. So if you win, and if you won the last time, you bet the same amount again. If you lost the last time, but you won this time, you bet the bet the same amount. But if you lose, what you do is you double your bets. So essentially, you try to immediately recover any losses, and that means that every time you lose, you're going to be betting more and more and more. And ultimately, if you have an infinite amount of money, you'll win all your money back, right? Get back on track. If you don't have an infinite amount of money, then you lose big, right? So that strategy actually works really well if you have a lot of money to lose. And then there's another strategy which is kind of a middle ground. All right. And here's basically just showing that the strategy works. We have plotting of the strategy. The strategy and right. Yeah, do you have, you probably
It's probably just Python.
just Python for you, so. Okay. It says it's busy. Okay.
Sometimes it's just easier to look at the
Okay.
bash. Bash. Command line.
Yeah, that's what I was gonna do, but it's your computer.
Oh, probably it's iTerm, not terminal, like the one that's way over there, yeah.
Seems okay. Control C.
Control C twice, yeah.
Lovely.
Just place that one and put it in here.
All right. Okay, so, yeah, yeah, because it's, it should say, the inline should come up first,
With the inline, so it's enough
behind the browser. There we go. There we go. Thank you. So here's the different strategies of what it looks like. Here's the one that bets the same every time, the simple strategy. Everybody starts out with the same amount of money. You can see, in the end, the bank ends up winning in that everybody loses over the course of 1,000 wagers. Okay, so this is 1,000 rolls of the die, a biased die slightly, just 1% biased, and the simple strategy loses. The martingale strategy did really well until you went on a bad tear and basically bottomed out, and that's how they all work. And then this medium strategy, the D'Alembert strategy, just tanked. So that's pretty typical of what you'll see. Okay, so that's good. And it's, while it's nice to have this descriptive code over here, okay, so while it's nice to have, this to plot it, it's also very useful as when we change the code, we want to be able to have some code that tests the code and gives you the results you're looking for. So one of the things I always try to make sure to do is write your code first, make it work, and then try to speed it up afterward. And basically, after you've written your code, make sure you have something that confirms the behavior of it. right? And the more granular you can do that, the better. So even though I'm looking at I have several different pieces of this betting strategy thing, which I haven't even covered all of yet. I have rolling the die. I can verify that rolling the die looks like it does what it should. I have this strategy here that we're plotting to see trajectories like this one, right? And you can see this one. The martingale actually did well and made a lot of money that time. It's pretty rare, but can happen. So it's good to have that code as verification. And you want to come back to that because when you make the changes to your code, you want to be able to check. Test code is better, but visual is good enough sometimes. And then last, well, not last yet, but we have, now this is basically just running one scenario. This is running one scenario, and then now this section of the code is taking the scenario and running it several times. So that's several players, basically. Here's Monte Carlo for our one bettor, and then we're going to be doing it for the number of players. So if we had 1,000 players, we'll basically do a while loop or a for loop across the betting as many times as we have players. Again, another place where we might have potentially embarrassingly parallel. There's nothing there that's any conditions whatsoever, so it should be easy to attack with parallelism. And then I have a bunch of things here that are checks, basically alive, profit, gains, and these are some analysis we're going to be doing for the next level up. So how many bettors were alive at the end, they basically weren't broke, how many people had more money than they started with, what's the total level of profit that was made, and what the percentage return on the investment. These are kind of important measures that we're going to have here. We want to have these measures because we're going to go one level above and try to do things like optimize the strategy based on some of these measures. So that's another level of looping above that. All these different levels of looping are potential targets for parallel computing. So here is using the trials. Here, the code to use the trials basically is another plot where it's going to run Monte Carlo and then plot it and then give me some feedback on how many people survived, how many people profited, what the average profit was, etc. And I can see here, I'll just use the one that was up before. For this particular run I had for the martingale, we had 15% survived. The average profit was a whopping loss, but the maximum profit did pretty well, right? And that is the martingale strategy in essence. Okay, so and the thing behind the martingale strategy is you double your bet, right? So one of the parameters you might change is, well, maybe you'd triple your bet if you lost, or maybe you'd do 1.5 times your bet if you lost. So you might want to optimize how much you bet back. Now here's the simple strategy, and you see there's a lot of survival there. 99% survived. Maximum profit was pretty small, actually, and there was a big loss still on average profit, so it tails down. So if you want to walk away with dollars in your pocket, it's a pretty decent strategy, but you'll probably have less than you started with. Okay, so this is our This is our loop optimize, where we basically have a metric here where, sorry. Here we have running the Monte Carlo loop and then calculating how many survived, profited, et cetera. And then there's a metric here for success. So what do we want to consider as success? Do we want to consider success as the number of people profited, biased heavily, weighted heavily versus the number of people that survived, but still taking those two things into account? Or we want to consider success to be this kind of formulation, maximum profit minus the mean of the average profit plus the initial funds. Whatever it means, we have to come up with something that that's going to tell us that's the thing we're going to target as important. All right. And then and then this is a nice, I did it somewhat hackily on purpose because that's how we code things, right? It's got some inventive Python things like a nested function inside of here that takes the metric and applies it, and then lets us only optimize over wins and losses, and then do IMAP, so essentially a for loop, iterative for loop over the function that's looking at W and L. So W and L is actually the amount you are going to be betting whether you win or lose in the strategy, right? So it's our multiplier, and that's the thing we're going to be optimizing over. And then there's another big for loop that's here that is going to run the thing. Well, actually, it's run a number of times in the IMAP, but the iterator pulls out the results in this for loop here. So we have a single for loop essentially that we're going to be working over. All right, and that will give us our that'll give us our ability to run several times, and then here, as it's being run, it basically prints out anytime there's a new better measure, and it eventually, this was the safety strategy, so the largest amount of people that stayed alive was 74%, and that happened at a 1.78 win-loss, where I'd tied the wins, where I tied the double down strategy. Basically, you do 1.7 times instead of double down, and that seems to come up as the optimal. And I've run this a couple times, and basically it's 1.7 something if they're both the same. So that kind of simulates what we might do in kind of our own scientific codes, something like that. And I will come back to working with this code. Hopefully you're able to run it, and if not, you can get the files out of the notebook and run them in the command prompt, which should work equally as well or better. Okay, so I wanted to go through a couple of the things that we should do when we go to parallel computing. Is first, like I said, prepare for parallel computing, and that means doing things like timing your code. So the things we want to look at are how do we get our tool set together for being able to do parallel computing, and one of them is time it, and just a simple timer, and another is the line profiler. So I've got some simple things to time here. There's a list comprehension, a for loop with an append, a for loop with a set item, right? So I'm basically building a list and then setting the item in the list as opposed to doing append several times. And then I'm going to time them. And from your instincts, right, from your instincts, what would you think is faster? Probably the list comprehension, I would imagine, right? That's what we all think. So we do, here's, I built a little timed decorator, basically, that all it does is takes your function and calls time.time before it and calls time.time after it, subtracts off the start value, and then saves it, stashes it away in a little dictionary that gets returned with your function itself. So this guy here, dec, is our decorated function, and it has a timed method that's attached to it, which is getTime, which calls this little hidden dictionary time and pulls the values out. So that's using some Python pointer magic to be able to have us save the timed value for the last run anytime we run this. And then, okay, so then here I have the main part of the code, and we aren't apparently going to be using the decorator right now, but we'll do the simple one first, which is time.time, do the list comprehension, time.time, do the append, and then we'll look at the results. Now, what I found for my own case was that list comprehension was the fastest, set item was the slowest, and there was append in the middle. Okay, so that's good. And just make sure things, because I didn't write it. There we go. Groovy. Okay, so so those are the kind of things we can do. Check the time of something. Now again, you typically don't want to be writing code checking the time as you're writing the code, because your most important thing is to get the code working first. Keep a lot of things in mind. You know, as you time things, you get to realize what's faster and what doesn't. You should keep in mind coding for parallel computing, which is for loops or map functions, depending on what level of parallelism you think you're going to be running at. Some things for loops are better in Python. It's better to write a for loop, and some things it's better to go vector, and some things it's better to go as a map function. And those are all basically different versions of the same construct. So here's now using our timed decorator. We have sum squared, which is just this little function that does a generator and then sums off of the generator. And we can run it, and then we can get the timed value, which is now hidden inside of our decorated function here. And we can see that it took 1e to the minus 5. And another version of this guy is, instead of using the time.time module, we can use IPython's built-in time it, like that, which is nice. I actually was a person who, well, still am someone who doesn't use IPython very much, and one of the things that I find I come to IPython for is the time it function. That's, to me, the most important thing that it has. So you can see that it runs pretty quickly. And we just want these things in our toolbox, right? So we want to be able to know they're there. We want to be able to use them as we go through our coding. Profiling our code is something, now that we have a piece of code together, we want to see, we want to see where hotspots are. It's another way of measuring the speed. So here I have I have a couple functions. Here is global, which is up here at the top. It's a global. And then here's a function that goes several times and then references global directly. Here's something that makes a local copy of global and then references the local copy several times. So you don't think of that very much when you're coding. A lot of times you put things up at the top and then you write code for serial computing, and it's very convenient for you to say, well, I don't have to kind of sully my code down here inside the function because it'll just look up the global variable above it. But that takes time, because what it's going to do is it's going to check the local dictionary first, and it's not going to find it, and then it's going to go to the next level up, and it's going to check that level, and it's going to go keep checking dictionaries until it finds it. So it actually takes a fair amount of time to do that. And a little trick to speed your code up is put a reference to the variable on the inside, and it actually can make a significant difference. Additionally, if you are going to be taking your code off to another processor and you're serializing a function, right? You're serializing only the things that are encapsulated within that function. So if you have references, which are global references, if you refer to another function within your function, it's not going to take that with you. Some serializers can go and grab that, but most of the time, you're not going to be taking that reference, and then that function is going to be dropped on another computer, and it's going to look it up, and it's not going to be found, right? So not only is doing something like this, which is you start to think about encapsulation not only for speed, but encapsulation eventually for serialization. So this global would still be a problem for that. Okay, and then I have two other variants with the same thing, except looking at true, the global true, which is a built-in, which should be even further up in the chain beyond global, and the same here. Right, and we can test that by calling it, and then here's a profile script. It just gets C profile, and it runs profile, and then it prints the stats for it. So we're running that over, calling it 1e to the 8 times, and you can see here the time of it. Repeat local as opposed to repeat, it's less, and repeat 2 as opposed to wherever the other one is. The local ones are less. You can look at the per call time. They're basically running it 1e to the 8, you basically gain a second, which is not bad, because the thing takes 3 seconds to 4 seconds. All right. Another thing you can do with the profiler is, here we have a little function basically, it's a pattern search string for web pages. So if you're going to crawl the web and search for things that you'd like to parse, you'd write maybe a regex parser string, and it's going to pull some code that matches that. And what we'd like to do is have this piece of code run. What it's going to do is have a list of addresses. It's going to loop over all of the the lines in your web code that you have, search for that pattern, and if there's a match, basically, then it'll add it here to the list of the addresses. So this profile decorator up there is intended for the line profiler. What we had before, when I just ran the profiler, cprofile, that is a function level profiler. So it can only profile at the function level. The function level profiler is very useful if you write 1 to 2 line functions. It's a good place to start to tell you which functions you should then line profile. So I typically start with well, most of my code is just 1 or 2 lines, and it'll tell me which one I have to worry about because you can run on the whole code. And then when you have the function that's slower, then you can use the line profiler to go after it. Basically, you decorate the function with @profile, and you decorate the function with @profile and run the line profiler. We run the line profiler like this. In the bash script, we do kernprof, L for do line profiling as opposed to doing function profiling, V for showing the results right away, and basically we're running it, and we get a printout that looks like this. Yes.
I get an error because the sample that HTML file is
Yeah, that I should have in that is the only file that should be in the repository that I didn't put in there. And
You should be able to dump any HTML file in there.
you could dump any HTML file in there, but I forgot to put that one in. Yeah, I'll, if this thing starts up, I'll put it in there, but apologies on that, I forgot that one. So what happens is I'll rectify that if I can. You run the, this will run, and you see the line profiler only profiles the decorated functions. So here we have a printout of our code, and then we have a line by line, basically diagnostic of the time it took to run each one of those lines. And you can see this function, 86% of the time is right here on searching the regex pattern. Right, so if we wanted to focus on one particular part of the code that was expensive, that would be it. Right, so that's very nice, right? So one thing you will not when you work in Python, you get kind of the idea of what's fast and what's slow. But I find that I'm often surprised. Right, a for loop has gotten a lot faster over the years. I started Python 12, 13 years ago. For loops used to be dog slow, and now you can kind of write a for loop and still be okay. You don't have to optimize as much because they use built-in iterators basically on them now. So the thing that I'm trying to say is don't assume something is fast or slow. Always always time, always test, basically. You should do this with profiling for everything. Anything that depends on speed, don't lose kern prof and line profiler and time it. Those are your basic tools. They let you not make assumptions about what's fast, right? This will tell you which is the slow line. Now it's your job to be able to figure out what to do to make it faster, right? So one of the things you could do to make it faster is then modify the code where here what we've done is precompiled the pattern first outside the for loop and then search the precompiled pattern, right? And then when you go through here, it's not compiling the pattern and then searching every time. So that should make it faster. And indeed, it does. I have the time of this thing left off somewhere. It was 0.0096 seconds, and now it is 0.0040 seconds, so that's more than twice an improvement. And you can see that the two lines now, instead of being 86% of the time, it's now 70% of the time, but it's better. And the nasty one is kind of taken out of the for loop. So you should use this profiler, and then you can keep working on it. Then now that gives you some other options. Well, maybe do I want to do something with either of these codes? And if you look at it, you might say, well, there's nothing I can do here with this for line in F, right? But you potentially could. So F is an object, and what you're doing is you're pulling your line out of F. If it's a list or a set, it's going to behave differently. It's going to be timed differently. If it's an iterator, it's going to be timed differently. So that's saying the construct F could be optimized to be faster. You can change what that is. Okay, so I'm not going to go into memory profiling, but there's two nice tools, Guppy and Pimple, there that are good profilers for memory. Now, you don't necessarily have to worry about memory in any of these things that I've shown thus far, but if you're going to be doing parallel computing and you're going to be using something like a NumPy array, NumPy uses a lot of temporary array space for speed, and then if you have a lot of big arrays, then all of a sudden your laptop gets really slow and starts to sweat, right? And that's because it's eating the memory, right? So you should think about using those, and they're all basically as simple as running the line profiler. So I already showed a little bit about global and local. Another thing that is a common case is called staying native, basically. Yeah. It's what? Yeah. Yeah, I mean, the point is just to check. Yeah. So, yeah, I'm not biased against 2 or 3, and I think I think the best thing to always do is just run the code. What I'm saying is just time the thing, and you'll always find out that way. So here there's the case of let's see, there's a list, right? We have some iterable coming in. We're doing a for loop over the iterable, and we're doing an insert. The same thing, an iterable coming in. We're doing a loop over the iterable, and we're doing an append. So they're two slightly different operations. Both of them are Python built-ins, right? The difference is so what I mean by a native method is you're not writing the insert method, you're using Python's insert method on the list. So that tends to be a lot faster than what you're going to write because those methods are written in the Python C layer, right? The data in Python is stored in the Python C layer, so the methods actually access the Python C layer, so they tend to be faster than your Python code you're going to write no matter how good you are. So the difference between an insert and an append is a list is structured in memory, and an insert is going in the front, and it has to move everything over. So it's an order n operation on the length of the list, and an append is an order 1 operation. Basically has to just hop another item onto the end. And
I don't think it's exactly order n. It's like Python list or like linked list, all those individually.
so I'm generalizing order 1, order n to roughly the length of the item, not exactly. That's it's fair to say 10 times n is still n.
Yeah, asymptotically though, I don't know if it actually scales like these techniques, but I mean, I understand it's
Yeah. Okay, so here is, instead of having this little for loop that we wrote here to do an append, what we might want to do is take the iterable and just directly convert it to a list. Okay, and now the difference is, are we going to go through a list and then add one item at a time, or are we going to use a Python built-in conversion to a list straight off, not loop through anything, and then basically the reverse is the same after that. So that says, should these methods be different, faster? This is not an order n. This is an order 1 operation, right? This is just a conversion of an iterable, and all of them are native methods. So now we're going to compare. So these are little functions that will compare them and use since they were decorated, they use the time decorator and basically gives you a ratio of what was faster. So we can look at it, and it's important when we're going over sequences or lists that you check it for the different length that you're interested in. If you're thinking I'm going to be running over small lists, then check small, and if you think you're going to be running over big, check big, because it does make a difference. Some of the operations scale, whether they're order 1 or order n, they'll scale by a different amount. So here over the small size lists, the order 1 to order n ratio, the insert versus the append is 2, and then up here in the larger size list, it's 23 times slower. But we'd expect that, right? We don't. Now for a list versus the append, the converting it directly to the list is much faster. It's native, right? It's a built-in operation going to a list as opposed to writing the for loop to convert to a list, right? So the more work that you can put inside of a function that already exists in Python and the less code you actually write, the better, right? So that's, I try to not write any new code whatsoever if there's methods to do it already, right? Because I always assume it's done better than what I can do. The only time I go and write new code is when the functionality for that doesn't exist. And that's basically what you should think about. And you can see here that the order one append versus basically the for loop versus the list actually loses some steam as the thing gets bigger, but it's gonna have to get pretty darn bigger to catch up to it. I don't know how big it would have to go. All right, so another bit is pointers versus copies, right? So Python runs on pointers, basically. If you know where the pointers are in Python, pointers are very fast. If you work purely on pointers in Python, then the speed of what you're doing can have C speeds. When you start making copies in Python, what you're essentially doing is you're taking data from the Python C layer and you're pulling it up into Python, and then you're pushing it back down into the Python C layer. And that's why things get a little slow, right? The data is kept in the C layer, so anytime you're making a reference to something else in the C layer, you're doing it fast through a pointer, and anytime you're pulling it up and creating a new object, it's going to be slow. So here we have basically timing of more constructs, a double extend, a concatenate, and we can just see the difference in the time it takes. Basically, here's another choosing the right container where do we want a list or do we want a set? So what's going to be faster, searching through a list or searching through a set, right? Searching through a list or searching through a set? Searching through a set should be faster. Matter of fact, it should be much faster. So that's searching through a list on average. If the item you're searching for is always first, the list will win most of the time, right? But if it's at the end, the list is going to lose badly. On average, the set should be much faster because it's a hash map, essentially, and that's what Python runs on. That's what a dictionary is. It's what the set is the keys of the dictionary, and that's where the speed lies in Python in lookups. So this should say, hey, the set's going to be fast. But what if most of the code that we have, the values are not contained within a set, right? They're usually contained within lists and whatnot. A lot of the nice constructs that we have compose lists or iterators on lists very easily. So a natural case is if we want to search for our data, search for an important member inside of our data, we know a set's faster. Do we convert to a set and then search through the set, or do we leave it as a list, right? And so then we can compare, and we can see here that actually this is the it is on purpose, right? I'm on purpose counting the construction of the set here. So in this case, searching through the set is slower, and it's slower for almost every case, for every size, for every amount of times we run it, and for every amount of elements that we put in it. That says if you have a set already, it's going to be fast to search, much faster. But if you have to convert to a set, you're better off searching through the list, right? So that could be a surprise. So, and then you can see that if you don't count the construction inside of the timing, as I'm doing in the next block, the set beats the pants off of the list, right? So make sure that you're going to be timing for the use that you have. Okay, so you could try this. Basically, write code that calculates the sum of all squares of the numbers from 0 to 1 million. Use a for loop that directly adds, basically as a sum with plus equals. Do it with a list comprehension, and do it with a generator comprehension. See basically how it compares. I think that's basically, can you build one of these time constructs? It's a fairly trivial exercise, but get your hands on doing it. And I think if you don't look too far down, you'll also see it sitting right there.
Did it work?
It's alive.
That's good.
Just taking a nap, seeing if it's all
Does it need some coffee?
We all know what kind of thing it is to lose a. Yeah. Okay. You can go to sleep. All right. Yeah, isn't that a surprise? Yeah, you do. And so that surprised me too, right? For loop is better every time. It did not used to be the case, right? So Python has gotten a lot better at using, so what happens when you write a for loop is the parser constructs an iterator for you on the for loop. And again, the part of the rule is to use Python's built-in stay native, right? Stay native. And now in writing a for loop, you're actually staying even more native than you are with a list comprehension and a generator, right? So that, when I saw this the first time, I was surprised.
Except for
Yeah, there are certain cases.
10,000.
Yep.
I just ran the list comprehension.
Yeah. Yeah. So again, you should not make assumptions here. If you look at the difference in the speed, it's not too much, but it's enough that if you're going 10,000 times, you know, it could make, this doesn't make that much of a difference, but it could make a difference if this was actually doing something that was more expensive. Yeah. It could. And don't make assumptions, time the thing, right? I mean, that's, on the Mac, which is the only place I've seen it run, I didn't try it on Windows. This is the same results that I got.
Well, I just did it on Windows again. Maybe, you know, I should close down everything else that might be open here.
I think this is what you get.
So what value of those that list coverage is constant number? Yeah, the list coverage is the one that.
Yeah.
I mean, is the argument now that list comprehensions are only sort of useful because they're compact? Because it's my understanding, yeah, that when somebody explains list comprehensions, like, oh, it's compact and it's more efficient than for loop.
Yes.
And that was 7 years ago.
Yeah, and so I have in the past converted a lot of my code that were for loops to list comprehensions. And now I'm looking at it and saying, well, damn. I've got to go back, right?
And this is strange behavior because, you know, I've run it twice, and of course, that's not much of an experiment, is it? But only on the third case where you're using 10,000 is the list comprehension the fastest.
Mhm. Yeah, that's what I got too, is the list comprehension is fastest in
One case.
the one case. So there's internal things in Python, right? So when you hit a certain limit, Python starts to do things with big dictionaries and overlaps memory and things like that. That's deep internal stuff. So you don't have to know all of that stuff, right? You just have, I mean, I have a good general picture of how things work, but time the code and there's no guesswork
We
about
don't
it.
have topic, we don't.
I don't think he's doing that anymore.
Probably.
All right. So now, in going to list comprehensions, people often think, well, you know, maybe I want to go to Numpy too, right? Numpy has vector code, so it's vector programming. Vector programming means that if I do an operation like A plus B or A times B, it's going to do it for all the elements. And matter of fact, Numpy is, again, the code is, in Python, the data is stored in the C layer. So this is operations on, you know, C buffer memory, essentially. And it can be vectorized, just like C arrays are vectorized. Numpy working in NumPy with vector code is very nice. You can get some native parallelism there. The biggest issue is actually going back and forth into NumPy arrays. It can be very slow in the overhead of building a NumPy array. So is that appropriate for your case, right? Here basically, here's some, working with NumPy, you have all the built-ins for NumPy like sine and max. So you want to use those if you have a NumPy array, you want to use it on a NumPy array. But if it's maybe a list coming in and you're doing a sine on a list, you hit a conversion penalty, right? So you have to think about, even though these functions will work on NumPy arrays or they'll work on lists, they're optimized for NumPy arrays. And even though I'm not timing it right there, will you lose time using the supposedly faster NumPy array or ufunc like sine or max as opposed to the one in the math library, because you're doing an implicit conversion to a NumPy array from a list as part of the process. Right? So you want to think about those kind of things. Anytime you're doing a data type conversion, you're going to be taking code out of one structure, out of the C layer, back into Python and back into the C layer again. And that's part of the slow process. You can do a lot of the neat things in NumPy, like here's an add, several different adds essentially. HStack is basically list concatenation, but in NumPy. There's add, which just adds each of the elements, and there's the cum sum, which is add accumulate, which is actually how the cum sum is built. So you can go and do a lot of newfangled operations in NumPy. And again, you shouldn't be writing your own math operation in NumPy in general. If you dig around enough, there's enough there, there's enough there that you should be able to write most of it using built-in stuff. Here's another common thing that you might do is you have some sort of construct that you'll run in a for loop for I and j and enumerate c and then do a squared. But I want it to go to a NumPy array. I need something to be done in a for loop for whatever reason. It's not a NumPy operation. It's working with non-NumPy numbers. Is it better to do conversion at the end? Is it better to convert to NumPy and then try to hack an operation? Or is it better to build a NumPy array and then fill the NumPy array inside the for loop? Right? So you have to go through these kind of choices. And one thing that I remember being told a while ago, and it's based on what I do in C, is you can build a void array, basically an empty array, and then fill those elements. And that allows you to have, you can see here, if you do a view, this is doing a view on the NumPy array. What I'm doing here is, instead of having to, every time I add an element to the NumPy array, instead of building a new NumPy array that's one element longer, what I'm just going to do is use a view on this big, long NumPy array that's empty, where I'm only looking at the part that's filled thus far. And the nice thing about that is that's kind of what you would do in C, right? You'd allocate an array with a particular size and then only look at the version that the length of it that's important. And if you know in NumPy that NumPys are views on C arrays, and a slice like this doesn't make a copy. A slice just produces a pointer reference back to the original. So this is also fast. So it's fast to make it look like it's a variable length growing array. We're only looking at the data. And this is, if I was just to write it, I would think this is about as fast as I could get it for a NumPy array that has to grow in size. Now I didn't time this, and you probably could time it and check to see if you could make modifications to speed that up at all. And it might be that you don't use an empty array. Maybe if we're filling it with integers, you'd use an integer array, and that might be faster. Oh, I made it a type int, so that was my best guess. But you want to be aware of these kind of things as you're basically writing your code, and again timing your code. And again, here's something like a VStack, which is a built-in operation in NumPy to stack these two arrays together, as opposed to you writing something to do that. Right? So you want to be able to, if you're going to be working with NumPy arrays, there's a lot there, and you should dig to try to figure out what operation you want to do and what it is, as opposed to writing it. If you're, again, worried about writing things in parallel, like we have our Monte Carlo application, Monte Carlo optimization, there's several levels of for loops. That means anything that's slow is going to be repeated n times. Matter of fact, n times over m times over O times over the top. Okay. So you should also be aware in things like NumPy, there's these two operations was produce the same thing. There's shape and there's reshape. Shape is just changing the index on the NumPy array, and it doesn't actually change any data. It just changes the view on the data. Therefore, it's a very fast operation. The amount of data it changes is right there, that -1 and the 8. It's just changing the view and doesn't touch the C data underneath. And then reshape, what that's doing is actually creating a new NumPy array and new data underneath. So the first one is changing an index, and the second one is creating a new array. And there's a lot of different operations. These flatten and transpose. Transpose does not create a new array. Transpose is just an indexing trick. NumPy is indexing on C buffer memory, where the NumPy array, as far as what we see in Python, it's a description of strides, essentially the number of times you have to skip points to go by rows and by columns in each dimension. And that's essentially what the NumPy array is, and then a pointer to the underlying data. And if you want to do a transpose is just flipping the strides, right? So it's just changing the indexing scheme, and doesn't touch the data at all, right? So I can take a 1 million element, 10 million element transpose in almost null time, right? Because it's just flipping 2 numbers, basically 4 numbers, depending on what size dimensionality it is. So you should be aware of the different types of flattening, which is also potentially, again, if it's a regular operation, which is stride, like a range, start, stop, and skip. Those kind of operations in NumPy are done by indexing usually, and that means they're working off just changing the stride index, not changing the original data, and you produce pointers. So those are all very fast C-level speed operations. However, as soon as you produce a new array, what you're doing is you're pulling the data back into Python and then back into C, and then you'll hit a speed penalty. So you should, if you're working with NumPy, you should get to know NumPy and what operations are fast. All right, so and this is basically just showing that it's pointer back to the originals. So there's two different good operations for indexing in NumPy. There's slicing, which, like I said, it's a regular operation, so it's strides. Therefore, since it's strides, it's basically just going to be producing pointers, basically, a different view on your data. It's very, very fast to do. But the only type of indexing you can do on those arrays is regular. So things that have a regular pattern to them. If you need an irregular pattern, then you can use the fancy indexing in NumPy, which is basically a where. Do I have a where? Yeah, I'll get back. So there's a where, and a where allows you to do a more generalized indexing. This says, I want to do X where X is greater than 10. So X where X is greater than 10 will give you all the indices in X where X is greater than 10. And then you can put this inside of a bracket. So I want X where X is greater than 10. And that'll actually give you the will not give you the indices of the values. That'll actually give you the values where X is greater than 10. And it's the same thing as writing, that's the compact notation in the bottom, X, where X is greater than or equal to 10. This, since it's not regular indexing, can't be treated as a readjusting of your indices on your NumPy array, and the result of that is it's creating a new NumPy array. So the penalty you pay for flexibility in your indexing and your slicing is speed, right? It ends up costing you time. A where is great, but in essence, it's expensive. All right, so here I timed a few things in NumPy arrays, and you can see things like this slice. Slice is pretty quick. Transpose is pretty quick. You can see the transpose and the slice. All these operations are relatively fast. There's add, where I'm not creating a new array. I am creating a new array. I'm doing an add of C and D transpose, and that is, as opposed to using the plus sign, it's using the NumPy add, which is uglier, but you should check if it's faster. Right? It's again NumPy on NumPy arrays using a ufunc, so I would expect it's faster, but you should try it. In addition, if you give a third element, add C, D transpose, and then say comma C, then that's putting the result of the add into the last element there. So if I was to say like this, I would take C and the transpose of D, and stick it into C, I'm not even creating a new array. I'm replacing the elements of C with the result, right? And that's all, again, staying down in the C layer and not coming back up into Python. So that should not have much of a speed change versus what's there, but again, you should check. All right, so there's where. Okay, so, and there's some fancy where operations. You can do things like this, X where you have the evens being replaced by the evens -1, right? So you can do all sort of fancy things with these indices, but again, it might cost you in speed. So let's look at something like this, vector programming versus looping. If we have a function here, the sync function, now there's a NumPy sync function, or we could write this in a more NumPy way. Here, this is not a vector operation. This is sync, where it says if x is equal to 0, return 1. This guy here is vector, right? It's written just like the math, sine of x over x. So this would be a vector function where it would work on NumPy arrays, except for this first part up here. Now, one of the NumPy should give you speed, and in many cases it does. The painful part about NumPy is often converting your code into vector code, and not all parts of your code are vector code. So aside from the time considerations it takes in going to execute your code, remember why we're in Python in the first place, is to write C code, it takes forever, and Python code is going to be slower than the C code, but you're going to be done first, and you'll probably have results first, right? So you got to think about those things too. And here, this piece of code, let's say I got it, but I wanted vector sync, and I could either work at turning this into a vector sync function, or I could just say vectorize the function. And this is actually a decorator you could use, at vectorize, and it will convert it into a ufunc, basically, for you. And then you'll have a vector sync function. And that's what the documentation tells you, that it'll be a nice NumPy function. And what it does is it works as a vector function. I can pass it a NumPy array like D, and it produces a NumPy array back at the end. But if we actually go and time the thing, how does our vector function do? Here's a map function on sync. Here's this sync function itself, and here's the NumPy sync. And you can see that the NumPy sync is fast. The map function on the sync, not vectorized, is faster than the vectorized sync function. But again, this is the cost of convenience, right? Instead of taking the time in programming, we used an auto wrapper to make it work as a NumPy function, but it cost us in speed, right? I've made that, yeah.
Well, I was just gonna, just take this back a little bit one further. Add another line there that says time at NumPy sin x divided by NumPy at max of x. I'm gonna look at that. Assuming we have the system problem.
Yeah, I wouldn't have guessed. But again, that's not what we're here for, right? Part of the lesson behind this stuff is you don't have to know all the rules. You should have instinct to be able to write the code. But I can tell you that I've used this before. There's very few times that I thought, oh, that's a cool trick, right? And I thought, okay, I'm spending 25 minutes trying to figure out how to rewrite the code. I'll just vectorize the thing. Of course, I write optimization algorithms, and I write code that's going to be called many, many, many times. And I have pieces in here that are maybe 2 or 3 vectorized functions that I now think maybe I should get that out of there. You know, now that I have time to go back and rewrite the code. But it's a nice convenience. So again, just like Python, we're paying in some regards for convenience. Although Vectorize is pretty old, and there are newer methods we'll see towards the end of the tutorial about things like Numba, which again do fancy things like Vectorize, which build C code for you, essentially. Okay, so here's kind of wrap this up as far as the intro part is you take the functions, roles, strategy, and trials, basically the die roll, strategy, and trials, the first 3 pieces of that. Profile these guys. And then see if you can see the hotspots. Are there any places to make significant improvements? So look at, the code is good code to work with, as in it's somewhat simple code. It's fairly modularized, and it all has test code. So it gives you the opportunity to play with it at different levels. Check it, see if there's any lines that are particularly something that you might change. And if you can, change the code and see what it does. I would suggest that you make sure to save the original versions of the code, because NumPy is not the end game, it's just the start. Some things in future ways we'll parallelize our code may work better with for loops as opposed to the vector NumPy arrays. So I would save the original and work off of a copy of the original. All right. So were we able to see some of the hotspots in there? There weren't too many, but I have kind of a quick look. I wrote here dice, rolled dice, where it's now throwing a vector, basically rolling vector operation here. So this now generates n random integers as a NumPy array. Okay. So I would think that would probably be faster. And then here's also many die, which we used as our test code previously, this for loop over the single die roll. But now I have this as a function that we might use. Okay, and then strategy, what we want to do is we want to take, I also did a version up here of vectorize win, just to see if that was faster, but we should know already that it won't be. The big difference is being able to roll all the die at once with rolled dice. And then in strategy, Here, I've taken trajectory and basically split my strategy up. So what we're doing with strategy is there's a portion in the strategy where it takes a die roll, and instead of doing each die roll every single time, as we're looking at the logic behind the code, we do all the die first. So what this does is roll all the die first, and then record whether we have an up or a down. So it's got to, since we're getting ones and zeros back, what I've got to do is convert it to plus and minus ones. So it converts all of the zeros to minus ones. Now, while this is going to be fast, I know ahead of time that I'm going to get some speed penalty here because this is a where, right? This is a where. That's where the zeros change to a minus one, but we'll see what kind of difference it makes. All right, so then there's another interesting thing that happens because this is not vector code, right? The rolling the die is vector code. That's very easily vectorizable code. However, in the strategy, what happens is you play the game until you go bust. And when you go bust, it stops. It breaks out of the loop. So inherently, vector code will probably lose in that case. What do you have to do for vector code if you want all of them to be run at the same time is you either have to ignore busting, right, and just calculate for everything for the entire length, as if play it out to the end, even go to negative money, and then afterward correct for filling it in with zeros. So what because if you use vector code, everything has to run to the same length. So what I did here, I thought would be the fastest, would probably be to just have it run throughout the entirety for everything, because it's vectorized, and then say wherever x went less than 0, just set it to be equal to 0 afterward, right? So what that does is it basically clips off the negative values to be no dollars at the end. And if we look at that strategy that I had before, the simple strategy where you wager the same amount every time, the vector code for it looks like this. I have an initial wager, and it's a one-line piece of code now, right? It's basically take the trajectory, which was roll all the dice, take the trajectory, which is roll all the dice, and then convert the zeros to minus ones. And then down here, do the cumulative sum, right? So cumulative sum essentially will give you your value trajectory over time. It basically, if you started to go up in your wager, then the next point will start from where you were in time. So that's perfect for that. And then we can and this is just working over the ones and minus ones. And then we want to multiply it by the wager, which because we had a simple strategy, it's just a multiplication by the same amount every time. It's a pretty simple vector expression. So far, so good. And this would be exceedingly fast, except the problem is at the end, if we go bust, then we have negative money, and we have to do this clipping off at the end to clip all the zero values negative values out to 0. So where we potentially lose here with the simple strategy is if you run this 1,000 times and 905 of the people go bust quickly, the vector strategy is going to lose, or should lose, I should say. I didn't test it. It should lose. But otherwise, it should win. Now, the simple strategy doesn't bust a lot of people, right? We saw it before, 99% survived. So actually, this should do well for us. Martingale, on the other hand, is not quite as simple. And matter of fact, I chewed on it for a while, and I couldn't get this thing to be, it's not inherently vectorizable. Parts of it are. This should tell you if you're looking to turn this thing into something vectorizable, it's probably not the right choice. Right? If you spend that much time trying to get it to be vectorizable, it's probably going to be slow anyway. Right? That's a good rule for you. Here is the vector martingale, and I got the first part to be vectorizable and the last part to be vectorizable and bits of it to be vectorizable, but there's still one part in here that says, all right, I have a for loop, and I'm gonna go over the for loop, and still there's some point where if I win, it's fast, and if I lose, then I do the vector operation on multiplying by the cumulative sum and the amount I've lost so far. And so this has to go back and check throughout the history of time up to that point, wins and losses. So a bit ugly, right? And when I profile this, I'll see that this line is definitely the nasty hot spot out of it. And I could probably split this up into two different lines and check and see if it'd be worse. But just from the sense of this, the vectorized version doesn't look vectorized. I can tell you that this is probably not going to be faster. But again, the best thing to do is check. All right, so then here's our simple strategy, our martingale, which we had before. I didn't convert to D'Alembert. Note, we could have done this, right, to vectorize it. We could have done that, but we know that this most likely is not going to give you any speed up here. It's going to be slower than just a straight strategy. Now, the thing that if the code above was not naturally vectorizable, it is naturally vectorizable, so this shouldn't get us any gain. But if it wasn't, then it might. So here's our code above, the Monte Carlo strategy. And this has the while loop in it. The only reason I brought this up is because I needed it to run this thing again. And so now I'm checking the runs, where the run is going to be using different strategies. So I get the initial time, and basically here I've set it so I can run a test with Monte Carlo at a martingale strategy. This is the non-vector version. I can do the vector Monte Carlo martingale. I could do the so checking vector versus non-vector of the martingale strategy. And then And then basically, I'm plotting the trajectories of both just to see that there's no difference, right? Not only do we want to check that one is equally as fast or faster than the other, but we want to make sure we get the same results back, right? And since we don't have a unit test, we have a visual test, we still code against our visual test, just to confirm that we don't have any changes. So basically what I get back is, right, there's another thing that you can do too, is because we're running with random numbers, a good thing to do is do this, seed the random numbers. So when we're doing speed comparisons, what we're going to be doing is comparing against the same runs as much as we can, right? So how fair is the speed comparison if you're running it and the first better dies really quickly as opposed to the other one making it all the way to the end, right? So we want as much amount of similarity as we can, so we seed our engines. So anytime we're doing timing, we should do that. Matter of fact, it's good for your test code too. You should seed all of your test code unless you're specifically checking to make sure that you have some ensemble behavior over a couple course of runs that you don't want to pin on a particular run. Okay, so what that does is it allows me to use trials, and I get 13% and these exact values, and I seed again, and I get the same results back, so I can get reproducible results off of random runs. And then I use v-trials, and I get slightly different numbers, which is okay, because they're different algorithms, right? They're different algorithms, they pick in a different sequence, but they're as similar as you can make them. All right, and so we still see that they're ballpark, and they make reasonable looking results, since, like I said, I don't have a unit test to check. Then I can just check the time. And here, I'm using random seed everywhere. I'm doing the checking of the time. I use Monty, and one of the things you could do with time it is specify the number of loops you're going to do. So I make sure that I even give them the same number of loops to run over 10 loops. And you could see that the vector version for the martingale strategy, which I said is not easily vectorizable, ends up being slower. It's 1 second versus, well, no, it's 2.5 seconds versus 96 microseconds, right? So that's terrible. So then I can go and profile strategy, and that's basically look at where in this I have hotspots, and what I actually find is that where is the hotspot? The hotspot ends up being in this one line, and the one line is roll the dice n times, right? Roll the dice n times, convert it to a NumPy array. So if we wanted to fix anything, that would be the line we might want to focus on. But that's good because we can vectorize rolling dice, right? We can vectorize rolling dice and not change our martingale strategy at all. We can do the rolls ahead of time and then go through the strategy by doing a lookup. And so then we go and make that change, basically make that change here. So now when we start the strategy, the first thing we do is we roll all the dice, and then we go into our strategy as we had before. Same thing with the martingale, roll all the dice, and then go into the strategy as we had before with just a lookup. And we go down and profile this again, and the code speeds up. The code speeds up, which is good. We can see that roll all the dice is still pretty expensive. It's 30% of the cost, essentially, to roll all those dice, even in the vector version of it, but we've made it faster. And that was pretty much the only blatantly obvious place we could have done that. Now, when I actually go through, now this is all the different versions, but when, see if I went back up and found the profile that we did, what you should see is that the martingale strategy is faster. Martingale strategy is faster non-vectorized, but the simple strategy is faster vectorized. So that was the one that is pretty much vectorizable, right? There's no, you wager the same amount every time. You do, you don't tend to die, right? The people don't tend to go broke. And so if you're playing the simple strategy, it ends up being faster to use the vector version. And if you're doing the martingale strategy, it ends up being much faster to do the non-vector version. Okay. So we go line by line, and all right. Okay. And then I can time, with my new case, I can time it and see essentially the speed that I get running off the entire Monte Carlo. And I'll just say we had a speed pickup. I wanted to see if this was the point that I vectorized Monte Carlo. No. Okay, so we get some speed by rolling the die as a vector first and then doing a lookup. So that really was the only place that there was significant win. Rolling the dice vector times and then replacing it in this strategy. So the frustrating thing about this is, you think, right, I'll push this code, and I should be able to, with NumPy, hard work to convert it to NumPy, gain some speed. May not be the case, right? We lost speed in the one non-vector strategy. So make sure that we not only time the code, but we know kind of what each represents. And the usual case for me is if it's hard work, it's probably not worth it. If it's easy, it's going to be fast. Okay, so now one of the things we want to look at is taking this code and this functional programming becoming a gateway to going parallel. So here we have code like add and squared, right? This is add two numbers and square. And then we could write this as one of these nifty little double list comprehensions here, right? So here's for I and j in zip x, y, add the values together in a generator, and then the values that come out of that, pick off I and put it into squared and get ourselves a result, right? So that's nested parallelism. That could be a nested for loop, but it's a nested list comprehension. Here's the same thing as a map function, map of squared onto map of add and x and y. That's nice, right? Most people don't use map. I like map. And the reason why I like map is inherently functional parallel, right? So one of the things that the most parallel, functional parallel code, not object parallel code, but functional parallel code. So when you go to parallel, you have essentially two choices. You can take your data and you can share your data across memory space or share the data across process space, or and then have the function everywhere access it. Or you can take your function and you can pass your function and your data everywhere by serializing it and shipping it off. The constructs that people use to do that are map and apply. Basically, map is batch parallel for a parallel map, and apply is a pipe. Basically, apply is something you don't see very much, and map is not something you see very much either. In the language, they were almost removed a few times, especially apply. However, they're such good constructs for parallel computing, that's one of the reasons they were left in. Okay, so this code, the reason I like this code is because for me to convert this code to parallel takes zero time whatsoever. I just have to inherit map from one of the parallel libraries, and I'm done. Well, that's done in quotes. You have to, some parallel libraries are better at it than others. But so this is a good construct, and we should check to see if it's equally as fast, as well as doing a list comprehension or a for loop. We didn't time maps before. Okay, so here is timing the map, and we see that the nested map actually beats the list comprehension with the generator, and we had to use zip in this case here. So the map is a more natural construct. There's less complexity to it for this, and it ends up being faster, which is nice because then it's faster serially and also naturally parallel. So that's good. And to see what I'm talking about, here's multiprocessing, which is Python's parallel processing library, basically, built into the standard library. And if you look at multiprocessing, has this little package called dummy for dummy threads on the inside of it. And it's the threading library built so it matches the same API as the multiprocessing's processing library. So if instead of learning the threading library and multiprocessing, you can learn multiprocessing and multiprocessing dummy, which uses the same API as multiprocessing. So you only have to learn one thing, which is good. And equally what that lets you do is it lets you switch between running thread pools and running process pools just by picking the different import, right? So this is a thread pool, and I have now a thread map, right? So I do a pool with the default number of processors on this guy here. It was 8. I don't know what this one is, probably 8. She doesn't know either. So here's our thread map, and now I do a thread map of squared over range 10. I do a serial map and then a thread map, and you could see that the serial map kills the thread map. So that depresses me because the thread pool ends up being one of the faster ones for small jobs. This tells me the best I'm going to do with this is not do any parallel computing on it whatsoever, right? That's because a thread pool has a number of things that go on, right? You have to thread lock. You also have to set up the pool. So there's overhead in parallel computing. There's overhead in parallel computing, and you should not assume that you're going to get speed gains. This is a tremendous speed loss in going to parallel, right? If you have written your code so you can easily drop in a parallel library and flip between the different parallel programming models like map and apply, then you can very quickly check which one's faster for your particular use, and then just use that one. So just so we don't get too depressed, we look at sleepy squared, where sleepy squared is squared, but it's going to sleep for 0.1 seconds. And if we time that one, then it took 1 second for the serial map basically to go through all 10 of these, right? 10.1 sleeps takes 1 second. And in threads, we have basically 200 microseconds. So yay, parallel computing, it did something for us. So that's the kind of check we want to make. And map is a very useful construct. Map and timing together. You'll find that you'll do the same things over and over again. All right, so here's my test the squared map code. Now, what I want to point out too is, while I've run these tests here, I'm running them in IPython. I did this just as an experiment to see if it would be nice, and hopefully it was not what shut me down here at the beginning, but I would typically run this out of a file, and I would put my tests in a file. And the thing that's nice is when you write a test script, you don't want to just write that test script and use it the one time to verify that the thing worked. It takes you almost no effort to save the thing, right? So the reason I brought up nose is that here's a test that we wrote, map and tmap give you the same results. We just time them above, but they also should give you the same results. So we can save this as a test. And then basically every time that you code something new, and we're Python coders, so a lot of times we code in the interpreter. If you code in the interpreter to verify that you're getting the right result, save that code, put it into a file as a test file. If you use nose, you don't even have to do anything else except name it test something, right? And now what you have is you have the validation that you did in writing the code saved to be used to check that code and make sure as you speed profile it, as you improve the performance of it, you always maintain that sanity of the code, right? So debugging becomes hard when the code changes and you don't know where the error comes from. But if every time you build, as you build the code, you're going to be profiling the code for speed. You're going to be building the code and checking to make sure you have the result right the first time. Save the code, and then you have efficiency for yourself in figuring out the sanity, basically, that your code has not failed to be sane in some portion, right? So you still get sane results. Yeah.
What is the benefit of nodes over testing
So not too much. So nose here does not have, where is the declaration of there being a unit test case anywhere, right? It just has to start with test underscore. There's a little fraction more overhead in the unit tests, but with nose you just have to do test underscore and it'll find it. It also will, if you run it on a directory, it'll find the tests in that, the test files and the test functions in that file. Yes. So when I write the code, I write test when I'm writing the code, I write the tests at the bottom of the file because then I don't have to open up 2 and 3 files. But then as soon as I'm done with that development cycle, I move them into a separate test directory. And matter of fact, the better thing to do is take them out of that test file, put them in a different test directory, and then run it. So especially if you're going into parallel, what you're doing is you're making it most like you've given the code to someone else, or maybe put that code on another machine or another process, right? So Python does some nice things on non-Windows systems about sharing memory, especially within the same file or within the same process. So the more you can remove that test code, the more valid that test code is for all sort of scenarios. So yeah, I do that. All right, so there's my test code, and I can run nose, and now I can make sure the thread pool is performing. Well, I mean, that's just an example of what you might write, but that cost me almost nothing to do, and now I have a verification check at every point. Okay, so another thing, when you're thinking about going to parallel, you want to look at error handling, right? Error handling is important. If you run parallel code and you run a million way parallel, and the last one fails, and it's a blocking map, guess what? You've just lost everything, right? So failure is bad. I mean, if it's an iterative map, you don't lose everything, but you might have to do a lot of cleanup because maybe your join, where you shut down the daemon processes that are spawned isn't called because it through a traceback. So this is bad. It's bad. Well, it's bad because something could go wrong here, and this could fail. The thing that will fail is sleep is not a module. So if I import sleep, then this will blow up. And we could see that it blows up with an import error. So if I was running that in parallel, let's say with multiprocessing setting as daemon processes, I might now just have 8 multiprocessing daemon processes that I have to go to the shell and kill all Python to shut down, right? And expect to do that when you go to parallel. Expect to become a system administrator and shut things down like that because it doesn't always clean up nicely. This is less bad because what I'm going to do is wherever there could be an error, I will check to make sure that that error doesn't happen. And if the error does happen, then it returns something sane. Okay, so whatever this is, it's taking X and returning X, but then if there's an error, it returns a none. Now I'm not returning X here if there was an error, because maybe sleep does something interesting, right? As opposed to just sleep. What I can do is return a none, and if it's a numerical calculation, I can identify which ones failed because there's a none that show up. And all of these runs will now finish. And matter of fact, if it's NumPy that's going on, there are methods in NumPy that allow you to ignore nans. So a nan is a nice value to throw in certain cases if you know you're working with NumPy arrays. So you want to think about if you're going to be running and you're going to be running in blocking parallel, can you do something that if this doesn't cost you too much overhead and it's going to cost you more to lose the run, you want to do something like that to make sure that it finishes and it provides you with an identifiable or ignorable result that comes back and let the job complete. There is, I don't write this a lot on my own scientific stuff because I can repeat it and it's usually not that bad, and I'm pretty careful with testing ahead of time. The more carefully you test ahead of time, the less you have to worry about something like this. But I have written some code in financial industry and flash trading where this stuff is everywhere, because if that goes down, people lose a lot of money. There you can't throw an error. It's better to have a slightly inaccurate answer so that there's definitely something you want to look at. Another thing you can do, and this seems simple, is I had you get PEP 8 pie flakes, or Flake 8, I guess it's now, and run these on your code. Right? If you run it on your code, what it'll tell you is, oh, you didn't do the expected number of white space or new lines at the end of a file or blank space, and you say, who cares, right? But here's another thing that's a common error, a typo, right? And PEP 8 and PyFlakes will catch things like, you have an unused variable, right? So your code compiles, you have an unused variable, and that unused variable is going to throw an error on a blocking map somewhere, and it's, or worse, undetectable error that's going to be run in parallel that eats memory or something like that. So you can catch a lot of these odd cases that are hard to detect with running PyFlakes and PEP8 on the code. So things like typos are typically, or poor indexing. Poor indexing sometimes can be caught. So those are, it's very good to check your code with that especially for parallel computing. All right, so another thing we want to do in going to parallel is there's going to be a lot of serialization, right? And with serialization, we're talking about taking a function and throwing it off on another processor or another something else, another machine. And we want to make sure that the code can do that. So code encapsulation basically means, let me see, I have a, code encapsulation basically means that while you're taught in Python not to do this, not to put the imports on the inside of a function, in parallel computing, it is the better thing to do. Okay? Because if you take this function and you throw this function off to another processor, and you have a global, here's a lookup to import and it's local, and then otherwise you would have a lookup to the global space for the time module. If you're lucky, it will find it. If you're not lucky, the function will fail, right? Everything that is encapsulated inside of that function, that means all the code, the names that are inside of that function are self-contained. They either come in the inputs, leave through the outputs, or are imported or created on the inside as part of the code. If you do that, you fully encapsulate the namespace, all the variables in a namespace, so you don't have any pointer lookups on the outside, relying on Python's looking up into the higher level directories. Your code most likely will serialize.
I mean, doesn't that imply that you're using some sort of parallel infrastructure where you're actually shipping a function
Yes.
to another? I mean, 'cause there are other, like I've seen MPI tests where it doesn't work that way. You run the same script on multiple.
Yes. Yeah, so there's two typical ways you work in parallel. One is it's shared object, shared memory. And the other is functional parallel. So that's serialization. Shipping, you either take your object and it's spread out and the functions just cross over, the functions live everywhere and they just cross over the shared memory. That's not how everything works. More often you have shipping a function off. Both of them are good for certain cases. You have shared memory and you have serialization of functions. For shared memory, you don't need to do that. But for shipping a function, you want encapsulation. This is definitely the case. It will fail in many, with Pickle, it'll fail. There's DIL and there's Cloud Pickle, which are advanced serializers. And they can do things like look up global references to dependencies and ship them with your object. But it's still much easier and more reliable just to make encapsulated functions. And it doesn't cost you hardly anything in time in the serial code. Okay, so here, this guy right here is a little check. It's part of the DIL library anyway, but it's a little check that's useful. Check pickle, and basically what it allows you to do is it make sure that that pickling will work, right? So what this does is this provides you with a forking pickle. And what I mean by that is it sends the serialized object off to another sub-process, right? So I'm doing what Windows does as opposed to what the other sane systems do, which just spawns another process and it actually shares the memory for objects that are created in the global space. But for Windows, it actually has to fork another process, and that shared memory isn't there for objects. So it's much more likely to fail for things that are not encapsulated functions. So this is a check as if I was shipping off to another machine or I'm on Windows. And you can see that we have here dumping a list, we get a nice pickle. Dumping the squared function, we get a nice pickle. But what you'll notice there is it says C main squared, right? And that's just a reference to squared, who was built in main. That should give your first indication of a problem. Is that a pickle is serializing by reference, and it was built in the interpreter. So when you serialize an object by reference and send it off to another process, unless you're on one of those platforms that shares that memory across all the processes, then it'll fail. So this will succeed on in in a multi-process environment on non-Windows systems and fail on a Windows system, or fail if we were serialize it to another machine, or if we shut down the interpreter and start back up. Right? So we want to look at things like that. Look at either know what the pickle does, or look at the pickle, or use check pickle here to see that it works. And there we could see that it failed because it's working by reference. Okay, so here's Sleepy, which is Sleepy squared. And now what we're going to do is write it to a file, as opposed to working in the interpreter. And all I'm doing is taking this function and dropping it into a file. So now, instead of referring to main squared, it's going to refer to sleepy squared. And we check the pickle, and it now works. Okay, because we've got a sane reference. So little things like that can help your code work in parallel. All right, so let's go to actually multiprocessing and multithreading. Yeah, so
Since it is serializing by reference, it's not actually.
so for functions inside of a file, it doesn't make a difference. For things that are not functions, it might make a difference. If you make a curry, if you make a function within another function, that calls globals. And that can cause bad news either way, right? If you're working in the interpreter, if you're working in main, typically when you're running things in parallel, you often run parallel at the top level, like the Monte Carlo simulation. It's going to be farming things out in parallel. And if the things you're farming out in parallel were defined in the same file as you're doing the map, you run into this problem. Right? So the point there is, if your payload, your target that you're going to run in parallel, to be more safe, should be in a different file than the place that the pool is running. That's safer, because it's a more sane import, even if it's by reference. Now, if people will do crazy things, people will put maps inside of methods of classes, and then just say class go, and take its state and try to ship the instance of itself to the other processes. You can do these kind of things with the right serializer, but it becomes always easier to encapsulate the code. So encapsulating the code, if you're doing something in parallel, it doesn't hurt you. It helps you. The speed penalty for putting the imports on the inside are much less than not being able to run the thing. Now, the smarter thing to do is to put that function into another file, but I can't force people to do that. All right. So here's a multiprocessing, and it's hello from another process. So here's a function f, and we print hello, and then now we built another process, and what this does is it says, I've created another process, spawned another process. The process has an anchor here in our main, and this function f is now going to be executed in that other process, sent off like I did in check pickle, so that check pickle is exactly what multiprocessing does on Windows systems specifically, but it basically does a popen and ships it off to the other process. And this piece of code here is serialized and then shipped off. And then the args are what's passed into here. So it's F of world, so you get hello world from the other process. And then this is killing the process, basically. Start is make the thing run, so it'll call hello world. And then join is to shut the thing down. Okay, so start it up and shut it down. And basically what you get is hello world, where this was printed from the other process. All right, so like I said, on Windows, multiprocessing spawns with subprocess popen. So on Windows, any of you who are on Windows should make sure to do this for multiprocessing. If you're working in main, you only have to do this in main, but if you're working in main, from multiprocessing, import free support. And what that does is essentially, that says, I'm going to put the appropriate locks on the different process that spawned. Well, it completes the fork, basically. You have an open fork, and it says you're off. So it's just a bit of code that runs sysexit and allows it to exit. So that's what you have to run on Windows. I won't put this everywhere in the rest of the tutorial. If you're on Windows and you're going to be running it, you should remember anywhere you're running in main to add these two lines. For running through subprocess popen, which means multiprocessing. With threads, you don't have to. With some of the other things that I'll talk about here for parallel, you don't have to either. Okay? So I mentioned there was data parallelism versus task parallelism, and that's the shared objects, shared memory, versus basically spawning things out, spawning functions on other systems. All right, so there's shared objects. There's a bunch of shared objects we can build with multiprocessing. We can build, multiprocessing provides value and array. So here's value and array. And these are objects that when we put them into another process, like we are here, process target F, so it's going to be running this function in another process. What it's going to be doing is it's be taking num and r, which are pointers to value and array, and these guys are shared memory objects. So when I build value and I build array, these are actually building constructs in C. And you know, if you've ever written Python to C bindings, they have these indicators here for what they are, right? So that's an integer array, and this is a float value, right? And these are C objects that are shared between all the different processes. So when I spawn this other process, this other process is going to write to A. That's the reference here to the array. It actually shows up in the spawning, the original spawning process, because it's shared between all the different processes. So then it calls F at start, and then join, it shuts down, and we can see we print the new values, and they're changed. Here, they're changed. Okay, so again, more shared memory is managers and proxies. So as opposed to these built-ins like array and value, you can basically ship anything with the manager, anything that's pickable. anything that's pickable can then be converted into this shared memory object. So we have this manager, and the manager is going to take a dictionary, and the manager is going to take a list. And then we have a D and L in the main process that are going to be our proxies for it. So we can interact with D and L in the main process as if they were the shared memory object. Or we could ship them off somewhere else. So these dictionaries and lists, if I pass the proxy around and we work with the proxy object, it changes the original objects, just like we did with value and array. This allows us to use, like I said, arbitrary type objects and have proxies to them that are shared across processes. All right. And so if you want to look more at shared memory, the docs here for multiprocessing are very good. You could do that. One of the more efficient ways you can use shared memory is to work with NumPy arrays. It's a little bit more complicated, but you see that you have multiprocessing. So the C-types library basically gives you C-types library gives you access to C constructs, access to C libraries. You can run, if you have a Python, like the Python math library, import math, is just a connection to libm, the C math library. And all it's done is in C-types, you load the math library and you call the C functions directly through C-types into the C math library. What that means is you have C-types constructs that have to be told, basically, what Python objects they relate to. And one of the most common cases is taking a NumPy array, which has its objects in C buffer memory, and converting those objects to essentially void pointers or pointer arrays. And so that is done in this particular case. It's very fast to do this. You can build a raw array. You can have NumPy C-types lib, say, convert that raw C array into a NumPy array, and now I have a NumPy array. Doesn't go back into Python, and it basically says the pointer to the C array that I had, raw memory, is now being pointed to by NumPy buffer memory. Okay, and that allows you to have the NumPy indexing scheme on that code, and because it started with a multi-process shared C-types, it's now shared between all the different processes. So this is the thing that MPI for Pi and other pieces of code use in many places when running basically with shared memory objects. You share the memory between all the different NumPy arrays. So this guy right here, these two lines, are one of the two ways that you do that. There's really only two ways that you set up this construct, and this is the simpler of the two. And then now that we have a proxy to the shared memory array that's set up as a NumPy array, we can pass the NumPy arrays to the thing we're running on the other process. And here we're filling the NumPy array with some value. And we have two worker pools that are set up, both running this same function, each on a different processor, but working on this same shared memory. Note, it's actually working on different elements of the array. So this is working on the first column, and that's working on the second column. Therefore, it's not conflicting with each other, which is nice. You don't want to do that. You don't want to have it fighting for the same bit of code. So we start both of the processes off, it does the job, and joins when it's done, and we print the array. And we could see that, well, not columns, but rows. One handled the first row, and the other one handled the second row. That you have to be aware of, like I said, if you're going to be working on the same, instead of splitting your shared object up into two pieces and ensuring you're not writing on the same piece of memory space. If you can do that, great, you don't have to worry about locking. But if you are going to be potentially writing on the same piece of memory space, you want to have sanity in things to happen in the order that you want them to happen in. Like you only have one process writing to the same memory space at the same time. You don't have collisions. So functional serialization ends up being pretty easy. Shared memory serialization is a little bit harder. It's okay if you don't have two things accessing the same space, but if you do, then you have to worry about locks, right? You actually have to physically apply things like locks. So you only have one write at a time going on in space. So here's a lock on a class. Here's basically setting up a process. There's two processes that start. You're going to be working on some worker, and then it starts up. And here we now have the join for all the active children. There is no lock. Okay. Okay. I just said, hey, it's an issue. If I cover it, I think I might cover it later. But note that you have to put a lock if you're going to be accessing with shared memory the same space. So this is functional parallelism, like the map function with point-to-point communication. So this is a pipe, essentially. And here we're hand building our own pool, right? We have a bunch of processes, and then we're starting all the processes, and then we, for all the processes that are still alive by the time we're done, we do a join on all of them. And this is basically what a blocking map looks like. Okay, it's ordered and it's blocking. That's the higher level construct that the map is. And here we run this, and it starts worker 0 is in process 1 and worker 1 is in process 2, and then it finishes, but this worked on each of those being printed on a different process. So we have above a pipe, we have, above a process, we have a pipe and a queue, which are constructs for shipping objects off to other processes and interacting with other processes. Here, and again, we here we have two different workers. Here's a worker that's using a queue, and here we have a worker that's using a pipe. We build a queue with multiprocessing queue, and we pass the queue to the queue worker. The queue worker here says, I have a queue, and I'm listening on this queue. And then the first thing I do is I call get. So get is a blocking call, and that says I'm going to wait until I get something put onto the queue. So what you have to start thinking about is you have to start thinking about working with multiple personalities when you're working on this code in parallel, right? The same bit of code is going to be executed by different processes. So down here in main is the one process that down here in main is the one process, and basically what it does is it start and spawns the other process. It builds a string that says Python rocks. It prints, hey, I'm going to be putting this on the queue, and it puts the string onto the queue, put. When it says queue put, then out at the other end of the queue, which is back on the worker here, it comes in off the get, right? It comes in off the get, and it gets this V, and it says, hey, I got Python rocks from my parent. All right? And queues are one way. Basically, as soon as that was done, this guy's going to wait here until, and block on join until the other process is finished. It finished printing, and then now he can move on. The second thing that's going to happen down here in main is it's going to set up a pipe, and a pipe is two-way instead of one-way. So we have the parent connection and the child connection. So you send one end of the pipe off to the worker process, and you keep the other one on the parent. So now I can start the process, and now when I start the process worker code is running as well as the main code is running. So main, basically, let's see what goes on up here on the worker. On the worker, it imports pickle. It says hello, hello, hello with a message, and then it says I'm going to be sending hello, hello, hello to the parent, and then it sends, and then immediately goes to receive, which is wait. Okay, so it starts up, sends a message, and then waits. Meanwhile, back on main, we start, we take a list, and we dump the list with pickle to a string. Then the first thing we're going to do is receive from the child. So now it gets hello, hello, hello. And it says, I'm going to send this pickled string, which is the pickled list, to the child. The child is blocking on receive. So this send goes. This moves forward with date time. It says date time is today, and then it waits here for the child to finish with the join. Whatever the child is going to do, probably print, I got the string. Let's see. It says, I got this string from the child, and then it unpickles it, and now we've sent the list object to the other process. Okay, so here, pipe worker sends hello to the parent. The parent gets hello from the child. It sends the pickled list. Pipe worker gets the pickled list, unpickles it, and now we have the list that has been sent to the other process. We're doing low-level stuff here, right? And in general, you don't do a lot of this low-level stuff unless the map and pipe constructs don't work for you. So sometimes they don't work for you when you have to do locking or when you're using shared memory. If you want to go to shared memory, you got to worry about all of this stuff. If you're going to do the easier form, which can be slower, but it's easier, that's doing the functional serialization, you don't need to worry about this. In general, you just use map and apply. Okay, here is a lock. So I have a lock, and now with a lock, again, this happens a lot in shared memory. You say, I need this to be isolated. So lock acquire and lock release says when lock acquire hits, it'll wait there until it can allocate and put a lock on all the other threads. So that is the only thing that's executing at that time. Right, all the other code is running in parallel, but it will say I have to wait until I can get this to be executed by itself, and then when you release the lock, it basically goes back to being able to run in parallel again. You can build a lock like that, and that typically is when you access shared memory that a lot of people are going to be pinging on, you'll do something like that. Okay. So there's another type of lock you can do, and it's put an event in there, and that's basically when this guy, it says wait for something to happen, and it's wait for a synchronization event, and that synchronization event is right here, set. So when you set that event, all that does is send a message up here that it's okay to move on. So you're forcing synchronization with this point here, starting this piece of code, and this piece of code being run at the same time. So it says that the processes can run independently at different speeds, but now when it hits this point, it's going to wait until the code gets to here. This guy hits set, that is triggered on the wait, and now they move off synchronously. So if you have to worry about that, that's what you would do. Now, most common case is essentially we're going to be working in a pool. And a pool is easy in that you create a pool of workers, and then you send a function like this, random mean, off to the other processes, and you split up the data, range 1 to 10, so that gets split up and sent to the other processes. And then you get your results back where this code was evaluated on each of the different processes. So that's functional as opposed to data parallelism. And here's apply, apply, the same function across one element. Okay, it does the same job as map, except it only works on one element. And then we close and join at the end. Now, what you'll notice here is I run pmap on random mean, where there's a random number that's being generated in here. And the thing is, it's not generating good random numbers. Okay, if I was to run this several times, this isn't the best call for it because it's taking a mean of several numbers and it's calling this many times. But if you go back and you put the NumPy rolling of the dice in parallel, you'll find that the rolling of the dice, while it works and is fast, it serializes the random seed and ships that random seed to all of the different processes. So the first element that all of them see is the same. Oops, right? So you often don't want that, but that's the default behavior. So you should be aware of that. If you have either NumPy random or Python's random, both of them will have the same behavior. So the thing that you should do is yeah, there we go. Here's our random walk, right? This is performing a random walk with a cumulative sum over a random uniform. And then when we do vectorize, we do a list comprehension, and we do multiprocessing pool, and we do a pool of walks, sending it off to the different processors. You see that the results that we get show that this is good serialism, this is good random numbers. These are good random numbers. That is not good random numbers. Okay? So generally, you don't want to use a random number generator in the payload unless you use this nice snippet of code which this is our check pickle, but here is random state. And what random state does is basically says, I can seed a random number generator across multiprocessing. So this piece of code I just dropped in here, that if you want to use it, you can if you do these things. But basically, what it says is regardless of the random number generator that you get, it's going to create a new seed for it on the different process, whether you're calling even the old Python 2.5 version or MP current process, get process ID, set that as the new seed, and then ensure that you have a different new random number everywhere by then changing the seed to include the time and some multiple. So that basically gives you a different random seed on each processor. It's something you have to do if you're going to put a random number generator in parallel. Okay, so let's see. So we had our map. There's variance on the map. Multiprocessing provides map unordered, which is one of the faster maps typically. What that says, it's an iterative map and it's unordered. That's truly embarrassingly parallel. I'm going to run. I will give you results back as an iterator where you can see. So I have a results object for I in results. We'll pull one object at a time off in whatever order it comes back. So you can get results in a streaming way. It has the same syntax as map. It just returns an iterator. And here now I'm having a for loop on this where when a result comes in, I check to see if the absolute value is less than or equal to 1. And if it is, I quit. And I don't want any of the rest of the results. Right? So I can do that. And basically here you could see that essentially it was a range with some randomness added to it. And 4, 8, 3, 2, 5, 6, 7, 1, and then I hit the value that's a quit. And so it's unordered, and it came in a streaming way where then I just here is clearing the results, the rest of the results, I'm just not taking them. Okay, now this is blocking right there. List results will block until it's done. But if you don't care about the rest of the results, you can just do a close of the join. Here's also asynchronous. So there's the same thing, except we're doing an asynchronous job. Now this isn't iterative. So in essence, it's non-blocking, but you can't get any results out until they're all done. So asynchronous, here we're running this code that says, hey, I'm going to check to see if the results are ready. Check if ready. If the results are not ready, run this for loop and keep checking until the results are ready. And when the results are ready, then get. If I did get here, it blocks on get. So typically, people will try to use asynchronous map when they actually want the iterative map. Iterative map might be slower. Generally, an iterative map is slower, but an iterative unordered map is faster. But again, time thing. Okay, and there's apply async as well for basically building an asynchronous pipe that is blocking when you get your result. And here I'm doing the get immediately after. So there was no point there. But here is my loop. Basically, I'm waiting. Now all the results have come back, and so I get my my result back.
So you have in a lot of these critical CPU count processes.
Yeah.
Core equivalent to CPU in that statement, or referring back to CPU?
So if we're using the processors, it's the cores, right? So this is 8 cores.
Is that CPU with?
Yeah, CPU count is cores. Yeah. All right. All right, so one of the issues there is a lot of people will come into this and they say, hey, this is cool, right? I'm gonna start using, we saw the Sleepy Squared, there was a significant improvement with threads. If it's a heavier weight job, you use processes, right? There's more overhead there, but it can handle a bigger job because essentially you're spawning another Python session to work in with a little bit of sharing memory in between. The issue quickly becomes, though, as you try to use it, you find that it fails a lot. I don't know if any of you have tried to use multiprocessing. I encourage you to write a piece of code now, just a little check function that does something, and try to run it inside of multiprocessing pool map, and most likely it's going to fail. I would say 95% of the people who write something in here, just as a test piece of code, it'll fail. And it fails because it can't serialize the code, and that's purely it. There's a lot of tricks that you can use. Like I said, make sure to put it in another file where it has the right reference structure. But you can also use a better serializer. So there's a fork here of multiprocessing called multiprocess that basically has better serialization, and that's all it has. It's just replaces pickle with the dill serializer, and it then allows you to do things like construct inline functions like a lambda and pass that off to the other processors, or take class methods and ship them off, or work in main because it actually will pickle the function as opposed to the reference. So what this allows you to do is a very important point. If we're already using the map method so we can flip back and forth between serial and parallel, as soon as the stuff becomes unpickleable, then we have to write specialized code that's there just for the parallel, just for it being able to be run in parallel. We don't want to do that. We want to write code that's the same serial and parallel, and we can just drop in the map that we want, right? So we want to be able to have the same code work identically on serial and parallel, and just changing the serializer will help us do that. Still, one of the issues here, though, is multiprocessing's map, and thus multiprocesses map, can only take one argument, as opposed to Python map, which can take multiple arguments, which is a bummer. So it's not actually the same interface, although we'll rectify that. There's another mechanism here. If you want to go to distributed computing, there's this code called Parallel Python, PP, and there's a fork of it, PPFT, which is, I guess. It basically, the fork of it uses not pickling, but it uses the dill serializer. And it does a lot of the same things that multiprocessing does, except it allows you to set up a server where that server can be on your local host, or that server can be on another cluster. Right? So it allows you to then do multiprocessing across to another machine across a socket through here, localhost and port. So here, server, and unfortunately, it doesn't use the same language. Server submit, it's doing all the same things, but it's not using the same language. So different API. Server submit squared of 5, that's apply. Okay. And then wait, and then finished is not a function call. It's a method. It's an attribute that gets dynamically populated to the right value. So it's a little bit different of an API, but it's essentially doing the same thing where it allows you to run on different machines if you like. So that's PPFD, and it doesn't suffer from the Windows it doesn't suffer on Windows from the problem of having to do freeze support. You can run it from anywhere. Okay, so there is running, and now there's a higher level package called Pathos, which is not as well updated as, well, it's not packaged as often, and that's my fault, as the other ones above. But what it does is it provides the same interface as the Python map for multiprocess, and PPFT or PP, as well as MPI. So it provides the same exact API for the different levels of parallelism with good serialization, which means what you get to do is write code like this, write sum squared, which takes 2 arguments, and have it run for, here's a serial pool. And the reason I'm using serial pool instead of just map is because it's exactly the same interface as the multiprocessing interface. So it has a close, it has a join, it blocks even though it doesn't need to when you ask it to block. So all of these provide the same API. Parallel pool does parallel Python, process pool does multiprocessing, thread pool does multi-threading. All the same API. So you can take code like this, build it for any of the different engines, and run the same code, whether it's serial, multi-threaded, with the server. I didn't include the MPI version in here, but it's the same thing. Okay, and that allows you to switch around between the different levels of parallelism very, very easily and quickly check. Matter of fact, it lets you write parallel code as serial code if you use serial pool. Make sure it doesn't fail. Check all the pickling issues you might have, and then step it up through. The only change you're making is basically using a different map. So there's basically all the different pools being fired. Okay. So here, Pathos provides you with a lot of the natural constructs that you'd work in as you code. So here's prime numbers. We have a function called isPrime. And this is just checking to see if it's prime. There's sleep add and sleep add 2. And here is a whole bunch of pools going on, right? So I can just write mapping code as if I was writing my regular bad Python code that I write all the time. Right, here's with pool as pool 1, pool map so it works with the with statement. Then I don't have to worry about the join and the close at the end. Here's another pool doing an asynchronous map. Here's with where it's doing a zip on the inside with another pool with the iterated map contained. So this is a layer hierarchical parallelism, right? So that's in a sense a for loop with a for loop on the inside with a for loop on the inside, all on different processes. So that's not possible in other packages, but here it's like the code we would write for serial code, right? It gives you the construct for nesting parallelism. So essentially it makes it easy to do hierarchical computing and start to work with things like programming models, which are basically models of constructing circuits. So here's another example of having a process pool and a thread pool. And here we're doing something like we had before, multiprocessing asynchronous map with a thread map, a blocking map on sine and cosine, where it's working over two lists that are being fed into the sine and cosine, which are then executing in different threads asynchronously across the main process. Yeah.
You may get this, but how does these things compare to like IPython?
Right. IPython parallel is similar. IPython parallel does not have the hierarchical parallelism. That doesn't have the same API as the serial code. IPython parallel uses 0MQ instead of parallel Python. IPython parallel will give you access to MPI, but it gives you access to MPI through spawning another, through the command line, through command line magic. Pathos can give you access to MPI from the same Python session. So there has been talks between the two teams on joining the two efforts together, but it's not happened yet. Anyone who would like to help, it is an effort that is known by both teams to be something that would be useful. So they're similar in Pathos can use SSH, just like IPython can use SSH as well.
You don't have an extra step of like an IPython, you have to do you have to start the cluster.
There's no starting of the cluster. Yeah, you don't have to do that. Now, you can with Parallel Python start a server somewhere else on another machine, but with this you don't have to do that to run locally or anything like that, no. Pathos is older than IPython Parallel. It's 10 years old. Okay, so I won't cover that it has pool caching as well to reduce the overhead. And that was about as much as I'm going to cover of the IPython parallel right there. There's another newer thing called Scoop, which is yet another one of, instead of now two, we have a third, but that's what happens with government funding. Everybody builds their own. So let's see. I guess, yeah. I will, do you want the option of, well, there's an exercise that I put here, and the exercise is essentially try to take what we have with the parallel computing as a for loop and turn it into something with a Pathos pool. It's relatively easy, and I'll let you do that in your own time. There's a solution right there too, if you want to look at it. But the idea with working on going from a for loop to a map is simple. The process is basically go for loop to a map, replace the map with a serial map, and then replace that serial map with one of the parallel maps. You essentially stage the code to parallelism without actually having to debug in parallel, which is terrible. Okay. I would take your for loop code to maps,
Right.
and then take that code to a Pathos serial map, a serial pool,
Right.
which provides your map construct. It gives you the same exact API as the parallel code you're going to. And therefore you don't debug any of your codes except for serialization problems.
Are you going to provide solution?
I saw, okay, yes, I have that. If I didn't, yeah, I'll drop it in after the class. I neglected to paste that. It's in Untitled 9, which is left with Untitled 12 on this laptop here. I'll put it in. Okay, so here's for Parallel Python setting up a server. You could set up a server on by PP server and then give it a port. And then basically you could see what happens if you run a parallel pool where you pass in a server. You're still working within the same API. The only thing is you have a new keyword which takes server. And then you can see that what it's going to do is it's going to split the jobs up between the different hosts, running in the current process and then being run over to the other process. So this stats gives you a report on where the jobs were run, and that could be on a different machine. Okay, so I won't cover some of the other flavors like 0MQ, which is, again, what's used. If you have SSH, you can get a tunnel, basically with Pathos Secure Tunnel, and Pathos Secure Pipe is an SSH launcher. So if you're on a non-Windows system, you don't need Paramiko. If you're on a Windows system, either for IPython parallel for SSH or for Pathos for SSH, you need to get SSH on your machine. And SSH on the command line, you either get Windows for Git or Git for Windows, which has, oddly enough, SSH in it, or Paramiko. One of the two. Well, either of them will work. All right. And the idea is try to make this simple to do. We'll look at the last little bit, which is actually MPI. I guess the main point I wanted to make about MPI is it's a pain in the ass. And I wanted to raise another thing here is large-scale parallel computing in Python is the outer regions of the world for Python. Okay, so MPI for Pi is a great library. It's hard as hell to build. It's been a lot better over the past year, but it's still not typically an easy install, and you got to get all the MPI libraries. It's MPI's fault. It's not MPI for Pi's fault, but it's the linking of everything with the MPI library, which is terrible. There's GPUs with PyOpenCL and PyCUDA. Both are fun, high performance computing type stuff. And again, they're the nether regions. These are the only things that cover this area. There's a little bit more in cloud computing. There's PyCloud, which is now cloud, which you have to pay for. Mr. Job, which is the EC2, I believe. And then Apache has the Mesos, Spark, Hadoop, Zookeeper business. So all of these are kind of frontier things. MPI for Pi is pretty stable. And basically here is a whole bunch of the exact same things that we did. I'm going to skip this stuff. It's the exact same stuff that we did with processing, multiprocessing at a low level, the same stuff, except it has a different interface, so you can't use the same code. And it works at a different level. It's MPI level, so it's faster. The shared memory works faster. It's a very C-level code. But it's a pain, essentially, to work at this low level. I wanted to point out that it doesn't have a pool. And additionally, if you run it, it doesn't run from Python. You have to run it from the command line. MPI exec, spawn 3 MPI jobs, running Python, running broadcasting. Okay? So that's hard on your workflow. There are a couple things that, again, we go through the same solutions as before. Better serialization, so MPI for Pi can take DIL, or it can take Cloud Pickle, and if you do this little magic right here, you get better serialization. You can actually work with cluster schedulers, which are pretty easy. You just create a job file. But that still doesn't help being run from Python. And it doesn't give you the task pool. Although Pyena, which is basically Pathos for MPI, same interface, allows you to have a task pool. And so does a newer piece of code, MC, which is Monte Carlo. It has MPI pool. And what that does is it gives a Python pool for MPI. The Pyena's pool works from the Python process. The MC MPI pool, you have to launch like this, MPI exec, blah, 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 blah. Okay. So again, there's still, if any of you would be interested, there's a lot of work to be done on getting MPI a little bit more streamlined into the natural bit of workflow. Now, here's showing that Pyena does some of it, but Pyena is still very, after 10 years, somewhat less stable than the rest of the stuff you've seen thus far. Right? So here's map on multiprocessing. The problem is it's speed issues. You have to do a lot of trickery to make it work within the same workflow. And that means it's going to be slower unless you're running on a super big job. But the reason you want to run from the same workflow is you might want to spawn large processes on other machines. So here's basically this running from the same workflow. And if you want to look at the MPI pool on MC, look there. So there's some issues that we have. Although, and here's the real tall weeds, is being able to interact with cluster schedulers with MPI. So only, you can do this in two things. You can do, I think IPython has a packet called IPython cluster helper, which helps start up some of the, helps launch job files on clusters, but again, it's done through the command line, and then Pyena has basically maps, the map and pipe constructs that work with schedulers, just like servers in Parallel Python. I will tell you that both the Pyena, the IPython, the MC version, even the MPI for Pi version, all of this code is finicky, hard to make work. Even though it seems fairly simple to do this, you have to do things like configure your shell environment to have the right work directory everywhere you're going, so you have right work dir set to the right places. in your environment. There's a lot of other things like that. We have to look at the MPI documentation to make it work. But then when it does, it will launch jobs across remote clusters on supercomputers and send off your jobs for you if you need to go and do that. But you can see why that might be a little finicky. So we're, like I said, in the deep weeds. So in the one, guess 2 minutes I have left, I want to show one thing. And if you haven't used Numba or Cython, you can do Numba very quickly. Basically, when we saw vectorize, right? We saw vectorize with NumPy to convert things to vector code. The thing that Numba provides, and it's thing that Numba provides is JIT, like this, JIT, instead of vectorize. And if you put JIT up here on top of this function that does nested for loop, or a for loop, and then here's JIT on top of Mandel, which does a for loop, and then here's JIT on top of compute fractal, which has 2 nested for loops. What it does is it converts it into bytecode, LLVM bytecode, and essentially is at the C level. So you've just built C code, basically, just by putting a decorator on the top. And then it's worth your while to write for loops, okay? So I can do that, and I can look at the performance. Here's a bubble sort. Here's a bubble sort, and then a JITted bubble sort. And you can see that the first time it runs it, n is 100, Numba is much, much, much slower than the Python for loops. Ouch. But then every subsequent, that was the first time when it was the first run, it hits it. There's a lot of overhead in compiling, jitting. But then every time after that, it's much faster. So 8e to the minus 5 as opposed to the speed we have 0.001, right? And it's getting faster every time it goes through pretty much, right? So the thing is, NumPy, the Numba is fairly new, and it doesn't work on all constructs. So you say, this is great, parallel, easy, JIT, I'm done, right? Now everything's going to be fast. Remember, you have a first overhead hit at the beginning, and then after that, the problem is it doesn't work on all the constructs. So what you'll do is you'll wrap Numba JIT on top of the code, and it'll say, I can't do it. Cython has been around a lot longer, and so Cython is essentially going to give you the same thing, except it actually builds C code itself, and it generates direct C code. You get a shared library, a .so. It's been around a lot longer, and it essentially can cover almost all the constructs. It's a little bit harder to work with. So IPython has gone a long way to make it easier to use. You can do almost all of it from the command line, but you can also do most all of it interactively from IPython. So there's a file, pyx file, which is not Python anymore, So this looks like Python, but it's actually going to be compiled to C. So you just write this Python code in a PYX file, and just like when we put JIT on top of it, what you do is you say setup build extension in place, and you build it so it builds it as a shared object. And that has to be, this is actually good. This is hard to find on the interwebs. So this is the magic for building a Cython module, just like we wrote above. And that will build it in your setup Pi, that when you do this guy, you build a shared library, and then you can do import Pi, you call pied and vector pied, and those will be C function calls, just like they were native built-ins in Python. And IPython gives you, if you do loadx Cython, then it gives you Cython up here, just like JIT, and it allows you to do this directly in the IPython console. It's a little bit slower than if you do it from the command line, actually. The compiled code ends up being slower. But that's what you get for convenience. So what I again suggest down here, and that's basically the long and short of it, is you should look at the Cython code. It's Cython documentation as well. It's not all just write Python code and then do Cython up at the top. JIT also has a variance with Numba, and there are things like add type information. So you can add things like yeah, here. If you add type information, cdef, here now we're defining types. We're passing in a type of an integer. This essentially is directives to tell C what type of variables to use. This makes it much, much faster. It starts to look more like C, but if you do these things, then the speed will go from something like 2 microseconds per loop to this same piece of code where it runs 2 milliseconds to 5 microseconds. And that was just by putting in type declarations. So anyway, I'll put up the missing notebook that I had, and actually, if you, I'm going to update these notebooks a little bit in spots they were a little chunky, and if you want to if you have questions as you go through some of this stuff, feel free to drop me a line about it. I develop a lot of parallel code and work with some of the other teams that I'm not part of, like IPython, and I'm interested in making the parallel environment in Python better. So if you guys are interested as well, feel free to contact me or the IPython team, or Scoop is the third, about any of that stuff. And thanks.